Problem 2. From the lecture notes, page 1 to page 50. Collect the definitions of properties of stochastic processes. First, Hw10 stationary processes. Second, independent increment processes. Third, Markov processes. Fourth, normal processes. Fifth, strict sense stationary processes. Sixth, white noises. Seventh, mean ergodic processes. Eighth, martingales. Explain your understandings about these properties. Example, the white noise is a process such that its values at different times xti and xtg are nearly independent. Actually, they are uncorrelated. By definition, a stochastic process is called Hw10 stationary process when its mean is a constant and autocorrelation is a function of time difference. Usually, when we just say stationary, then we mean Hw10 stationary. Poisson increment process, Poisson impulse process, and random telegraph signal, these are Hw10 stationary process, and which are not. For example, Poisson process, semi-random telegraphy signal, and random walk, and the Wiener process, those are not Hw10 stationary process. If a function xt is strict sense stationary and ex squared t exists, then we can see that xt is also Hw10 stationary. But when xt is Hw10 stationary, then xt is strict sense stationary. This one is not generally true. Hw10 stationary involves only first order and second order moments. Second, independent increment process means xt1 minus xt2 and xt3 minus xt4 on non-overlapping intervals are independent. So from the definition we can see that independent increments, it implies uncorrelated increments. And also what we learn is independent increments process are Poisson process, random walk, and the Wiener process. Third, we see that a process xt is a Markov process if the past has no influence on the future when the present is known. For Markov process, it's also known as Markov chain. We can see that if we know a sequence is a Markov chain, then it is statistically determined by its second-order probability masses. So, we can know that Poisson process, semi-random telegraph signal, random walk, and the Wiener process, those are all Markov process. So we can know that there is some relationship between Markov process and the independent increment process. Then let's look at normal process. A process xt is said to be normal if the random variable xt1 to xtn are jointly normal for any n, any t1 to tn, such as this function. This function definition are from the lecture note page 27. We can see that from the function, the statistics of this normal process is completely determined in the term of the mean, which is eta t, and the autocorrelation are t1, t2. Usually, eta t is a function of t, and we use the Wiener process as an example to show that how this normal process works. Fifth, a process is said to be a strict stationary process if its statistics is not affected by a shift on time axis. For example, any sequence of the independent, identically distributed random variable will be the SSS process. But we know usually this condition is very hard to meet. Also, there is another property that when xt is a SSS, then we can know that fx xt equals fxx. When xt is SSS, then ext equals to eta, which is a constant if there is a eta exists. If xt is SSS, then we can see that fx x1 x2 t1 t2 equals fx x1 x2 t1 minus t2. The last property is when the xt is SSS, then rt1 t2 equals rt1 minus t2 if there is a ex squared t. 6. White noises. A stochastic process Vt is said to be a white noise if EVT equals 0 and RV T1 T2 equals QT1 delta T1 minus T2. Just like it mentioned in the problem, the white noise is a process such that its values at different times xti and xtg are nearly independent. Actually, they are uncorrelated. 7th, a stochastic process xt is said to be mean ergodic process if limit function from t to infinity 1 over 2t integral from negative t to positive t xt derivative t equals ext in mean square sense. For this process, we should know that first, ext must be a constant, for example, eta. Then, mean square sense means that the function, limit function t to infinity e 1 over 2t integral from t to negative t xt derivative minus eta square. This function should be 0. And when a wide sense stationary xt is a mean ergodic function, if and only if the function limit t to infinity 1 over 2t integral function from negative 2t to 2t c torque times 1 minus absolute value of torque over 2t derivative torque, this function should be 0. Then we can know that if xt is WSS and integral from infinity to negative infinity, absolute value of c torque d torque smaller than infinity, then this function is mean ergodic. Second, if xt is WSS and limit function torque to infinity, c torque equals 0, then xt is also mean ergodic. A stochastic process xt is said to be a martingale if ext on condition of xs equals x1 equals x1, where s is smaller than t. In probability theory, a martingale is a sequence of a random variable. for which at a particular time the conditional expectation of the next value in the sequence is equal to the present value. There are two examples of the martingale process, which are random walk and Wiener process.